Welcome to this lecture on microprocessor 8085 instruction set. We'll discuss about the programming in 8085, instruction types, mnemonics, and the use of instructions. Let's start. Before actually knowing about the instruction set of 8085, we need to again refresh about the electronic machines, digital machines in particular, that they work with the help of binary codes. And in programming type of machines, the machines which are programmed are programmable. They work on binary codes. Those binary codes are in nibbles, a set of 4 bits that gives rise to hex codes. And the binary information in general in microprocessors is handled in such type of group of 4-bit codes known as hex codes. These hex codes are zeros and ones, and the data which is associated with such type of hex codes which are kept for instructions are of the same shape and character. So when both codes will be present in hex, the instruction as well as data, it becomes a hectic job for a programmer to program an electronic digital machine. So for that purpose, some short names have been suggested, and those short names form a language of microprocessors known as assembly language. What an assembly language is based on the English type of reserved words. Those words are English type words, but when we translate them, they are basically hex codes, or they are binary information. But with such type of exercise, what happens that we can differentiate between the data and the instruction. The hex codes, which are now represented by an English type of word, are terms as opcodes or mnemonics. So what a mnemonic is shown in the example. like moo, call, these all reserved words are mnemonics. What a mnemonic is basically is a convenience for a programmer. These all mnemonics are translated by a device, by a program called assembler, which translates them back into hex codes. So the confusion of that, the mnemonics will be there and hex codes will be there. So this is only for the convenience of the user. Inside the machine, the hex codes for data as well as the instruction are executed. If we talk about the instruction set of 8085, the instruction set of 8085 is based on the 5 types of the instructions present there. We'll take them one by one. The first type we call as data transfer instructions. In this type of instructions, we have the data movement from one register to other register, from and data to a register or memory. So these two tables show the data transfer from register to register or register to memory. The hex codes are also shown here for every type of move instruction. The data transfer is also associated with move immediate instructions. The difference between move and move immediate, what we call as MVI, in those MVI instructions we have the immediate data also associated with the instruction. So if we talk about move, it is a single byte instruction. Only the hex code for the instruction is to be given. The transfer of data from one register to other register or one register to memory or memory to register takes place. But in move immediate MVI, we have an associated data byte which is available there within the instruction, that one hex code MVI will have its own hex code, and then other hex byte will follow, which will be taken as the immediate data associated with the move immediate. In the same way, we have LXI. LXI is also the move immediate, but it is long in the sense that the MVI takes one register of 8 bits, but LXI takes the register pair, that means 16 bits, 2 registers at a time. So when it moves data of 16 bits. So MVI is a 2-byte instruction, one for instruction and one for data, but LXI is 3-byte instruction having one instruction byte and 2 bytes of data associated with LXI. So there are other load instructions, extended load instructions, or loading HLPA, or loading accumulator. Oh, these are other load instructions also. Then we have the stack instructions, push and pop also. They are data transfer instructions. In the same way, we store in the memory an extended register or a simple STA, storing the accumulator in the memory. Then we have the in-out exchange or XTHL instructions. They all come under the data transfer type. The next type is arithmetic instructions. In the arithmetic instructions, we have the addition instructions, in which we'll see add B, add C, add D, and so on, add memory. So these all add instructions are meant for that they add B will add B to accumulator. So all those instructions of simple add or ADC, add with carry, they add a data of the particular register to the accumulator. Then we have the other type, ADI, in which data addition is taken and immediate data with what the accumulator data is to be added is given within the instruction. So add B, add C, add E, add H, add L, these all are 1-byte instructions. No data associated with such type of instructions. But with ADI, we need to have the immediate data being provided there. Then we have the DAD type of instructions. DAD type of instructions is the extended addition of 16-bit type of. So DAD B means BC period, DAD D means DE period, DAD H means HL period. So this is an extended or 16-bit addition. So then another instruction, DAA, is a special instruction for changing the accumulator contents to decimal. It will be in hexadecimal always. So when at some time you want to change it to decimal, you give DAA instruction. The contents of accumulator change into decimal form. Then we have the subtract instructions. In the similar way, the simple subtractions, subtract B, C, D, E, H, L, the same way. And then another instruction, subtract with borrow, SBB. And we have again the additional SUI and SBI, subtract immediate. Then we have increment, decrement instructions. These are all 1-byte instructions. So next type is the logical instructions. In the logical instructions, we have AND, ANA, means AND with B, then AND with C. These are logical AND instruction. Then one is ANI as AND with an immediate byte, and the accumulator with immediate byte given within the instruction. So this will be 2-byte instruction. In the same way, we have the logical OR, we have the logical XOR, we have logical comparison, we have logical rotate, and in this we have RLC, rotate left with carry, RRC, rotate right with carry, then simple rotates, RAL, rotate all left, RAR, rotate all right. So some other logical instructions like CMA, CMC or STC. In the branching instructions, where the simple or conditional jumps, jump, simple jump, and jump on non-zero, J and Z, jump on 0, JZ, jump on carry, we have jump on odd parity, and then we have jump on even parity, we have JP, and jump on positive, or we see jump on plus, and then JM, jump on minus or jump on negative. So we have PCHL for loading program counter with HL register, and we have the calls, the simple calls and the conditional calls as well. Call on non-zero, call on 0. So we have all types of calls on parity. We have call on plus, call on minus. Then we have returns and returns with the same conditions or similar conditions. Return on non-zero, return on 0, return on non-carry, return on carry, return on odd parity, return on negative parity, even parity, return on plus, return on minus. Then we have the interrupts, what we call as software interrupts. There are certain memory locations where some reserved programs or short programs are returned. Calling these programs or a particular set of instructions together, it performs a particular task we call as restarts. There are 8 restarts from RST0 to RST7. These are also coming under the branching because we use them to move towards a particular location where a short program will make a restart, type of restart out of these 1 restart. Out of these restarts, one by one we can execute them for different purpose. Then we have the control instructions like NOP, doing no operation, halt. We have then DI, EI, and then we have the masking instructions, RIM and SIM for interrupt processing. And this is all about the instruction set. Thank you very much.